Okay. All right. So thank you very much for inviting me. It's actually a pleasure to be here, and the program looks really, really exciting. What I have to admit, though, is I have to apologize that I'm probably a bit off key with the talk that I'm about to give here. I initially had planned on talking something that's a bit more in line with the conference, but we unfortunately weren't able to finish that project in time. So I'll talk about the different research project that I've been working on recently. So which is joint work with Yunxiao Liu, who is a grad student in Umesh Vazirani's group in Berkeley, Srinivas Arunachalam, who is a research staff member at IBM, and myself. And to set a bit of background for that topic, so what we're essentially interested in are potential near-term algorithms that run in a rather restricted setting, and for which you can still show that there's some meaning to actually running those algorithms on a quantum computer. And to give you a little bit of background, so what do we mean by these near-term devices and so forth? They're very restricted, and so then in the lab, it's a bunch of physicists that build a superconducting chip with a bunch of qubits, and they naturally decohere, as we all know, and they become less usable as quantum computing devices. And so one approach to actually then trying to find something meaningful with those devices to do would be essentially to just restrict yourself to short depth circuits and say, well, I have some coherence time of the system, I'm just going to truncate that. And whatever I try to do, I'm just going to try to fit it into that device and try to make it work with as best I can. And so one setting is exactly you choose very shallow circuits where the shallowness is determined by the noise rate. And then there's other means that are not using error correction where you try to at least fix the output of that circuit to within that limit where you have to restrict yourself, so you're not going to be scalable. So the entire goal in that setup is actually to come up with algorithms that are conceptually very, very simple as possible without being trivial. Okay, and then the hope is that you might be able to show something meaningful doing there. So there's obviously great interest in seeing whether quantum computers can do anything for machine learning problems. And a lot of heuristics have been proposed. Most heuristics come without any formal guarantee of whether they're actually going to be able to do anything better than a classical machine learning algorithm could potentially do. But a heuristic I'd like to basically point out are basically the idea of using your little short device to actually use that as a feature mapping device and to use that to estimate quantum kernels or kernel entries that are used quite ubiquitously in machine learning problems. And so there were a couple of years ago, there were two papers. So the one by us, another one by a competing group, which has a slightly different definition than ours of what we believe a feature space to be. And I'm mostly going to spend some time in giving you some background and motivation where that comes before we actually talk about the actual result in the end of this talk. Okay, so what do you want to do with it in a supervised learning setting? Suppose you have two distributions with two different labeled samples. You draw various samples, and what you try to do is, based on that, you have some cost function that you minimize, which is an empirical risk function that tries to minimize over possible candidate functions that is able to predict is able to predict the labels of new data points that this function hasn't seen before, right? And so a classical example is you have some input that comes from a distribution, you feed it through a neural network, you can train that neural network, and out comes a label on whether it is distribution P or distribution Q. And so what people have proposed in that sense, so this is not what we're doing here, but it's sort of the motivation of where we came from initially, is what people have proposed is, one idea is maybe you can use these shallow depth circuits to basically emulate what classical algorithms do and so forth, and it maybe gains some advantage in terms of what a quantum machine learning algorithm would look like in that setting. And the idea here would be you follow this sort of the steps, naively follow the steps what machine learning algorithm does classically with a neural network. You have some step where you load up the data, then you apply a variational circuit that you optimize over some rather complicated energy length surface, and then you have basically an observable that you measure in the end, and based on the output the statistics of that observable, which is a binary observable, you assign a +1 or a -1 label, and then you basically train that on very vary the potential surfaces. So one trivial example is, say you start basically mapping the data. Say you have, like, what is it, 5 qubits, and then you rotate those 5 qubits by a fixed angle, real value, and so you end up in the product state. Then you can apply your favorite really fancy variational circuit that parameterizes a bunch of gates with a few parameters. You measure the parity function, or an all poly Z string in the end, and then you basically collect the output statistics, and then we see more +1 outcomes than -1 outcomes. You declare that to be a +1 labeled example in that sense. And so a lot of people actually studied that numerically and exhaustively searched about different ansatzes and so forth. But if you allow me, let's make a really short break and have some review of what people actually do classically. And classically, there's one very, very, like, the first tool for which some actually formal results could be shown, which were classical support vector machines. So in the simplest settings, so imagine you have like 2 point clouds, one on the left, one on the right, and you want to come up with a classifier. And the simplest way you can classify that is by just drawing a line that separates those 2 clouds. And everything that's on the left of the line is +1, everything to the right of the -1. There are many such lines that you could draw. And there's a reason to believe so there's an upper bound on your generalization error that can be stated in terms of that margin of that line towards those two data sets. So the best upper bound that you can obtain is basically by trying to maximize the margin of that line relative to those clouds. So it's consistent. And then if you have a new data sample, you just check on whether it's to the left or to the right of the cloud. That's essentially the basic idea of what a support vector machine does. The thing is, however, that real data is considerably more complicated than that. They're not just 2 separable point clouds, and they're really, in general, not linearly separable. So the main component that makes this actually viable or interesting is something which is called a feature map. And what it does, it basically takes data initially that is not linearly separable, maps it nonlinear to a very high dimensional feature space. Then you hope that data becomes separable. So in principle, that can be an arbitrarily dimensional space in which you mapped. So the question is, so how do you still solve the optimization problem? And since the original problem of maximizing that margin can be rephrased as a convex optimization problem, which is a quadratic program, you can actually write down the dual problem. And the only problem that you basically then in the dual problem optimize over the Lagrange variables, and which is a concave problem. And the only thing you need to basically access that very complicated feature space is essentially just the inner product between feature vectors. And these inner products are basically, they're referred to as the kernel function. Okay, so now so much for the very short background of what a support vector machine is and what it does. If we go back to these very fancy quantum neural networks, well, you can look at that for a second, then you make a very simple observation. If you look at that, what is the decision rule? So if one frequency, basically see in +1 labels more than the -1 labels, if you assign it based on that, the dominant thing is essentially, well, if you write out the probability measure in the large shot limit, then you realize, okay, you can actually just read this as a linear separator where your observable arbitrarily rotated by that circuit just acts as a linear separator in quantum state space with some normal. And the feature map would be just the initial part where you loaded the data in. And so what you observe there is essentially, well, it's actually just that inner product. So it's just a linear threshold function anyhow, what you've done there. And so doing that, you can probably find a better separator as long as you can compute the kernel. And if you look at the kernel that we initially had, it's just a product state that a lot of people propose, or that you can propose in general. So if you just multiply that out, you can compute that kernel in linear time, right? So you would be in that case way better off just using a classical support vector machine, evading the problem of having a variational circuit, evading the problem of not being actually able, having all these sampling problems, and actually having a convex optimization problem. So what is it that you learn from that? Well, how do you save something like that? And so the idea to save that is basically, okay, let's make the first naive step. Let's try to at least come up with a kernel function or a way of how to map data that is not classically efficiently evaluatable, right? And so what you could do is you could imagine there's some interesting unitary circuit family that you could use. And that unitary family that depends nonlinear on your datum sort of acts as a feature map. And then if you basically look at what the kernel would look like in that setting, it's essentially just the transition amplitude from going from 0 to back to 0, basically by applying ux and then the inverse for different data point u dagger xj. And then you just count how many zeros you see. So this is very, very simple. The rest you would do everything as you do classically, but it sort of fits in this extremely simple setting of where one wants to try to show some form of, to come up with some form of a quantum algorithm that does potentially something meaningful in that setting. Okay, so to summarize, what were the main observations? Were really simple observations where, well, the first thing is that the quantum neural networks people, that the heuristics that people have been using quite a bit, they're actually just immediately related to standard linear classifiers and can be equally well exploited if you use kernel methods. So there's no real need of actually doing them. The next thing is you can only hope to actually gain something in this setting if you would start with a quantum feature map or a circuit where you cannot estimate these kernel functions efficiently, where estimate is up to an additive sampling error. You wouldn't be able to estimate them efficiently, and that could potentially give you an edge. And a neat thing is if you skip all the other things, so if you skip the fact that you're working with a quantum neural network and so forth, you actually have now a convex optimization problem. So you know that the object optimization of the problem is not actually the problem anymore. Okay. So all that said, the question is now. This is a necessary thing for this to be non-trivial, but coming up with a different kernel, is it actually also sort of sufficient? Is there like at least one example where you can show that an approach like this would actually give you a result where you say, okay, there is maybe a way of classifying data that is sort of on par with what you would do on a classical machine learning within a classical machine learning algorithm, and the input is the same way. You have classical input and so forth. Is there at least one example where following this approach, can we construct such an example, actually gives you a provable advantage over all possible classical classifiers that would like to say to classify that data? Okay. And so what we have to do here is basically we have to go and we have to construct such a problem. May it be artificial, as it's going to be very artificial, the problem, but at least it's going to allow you to show that all these steps follow and that no classical learner is actually going to be able to guess the labels correctly. Okay, so let's go a bit more into the basics of how you classify. There's a couple of concepts. So there's something called a concept class, which is basically the set of all the functions that we just talked about earlier that you try to train over. And this is what you try to learn. The next thing is, are these training samples that are given, meaning you're giving the sets of samples that come from two distributions. You assign them labels according to that to one particular concept that you try to learn. And then you have something that you aim for comes from the PUC setting, is basically you try to declare test accuracy that with high probability over those two distributions you draw the data samples from, you want to have that your prediction agrees with the actual ground truth label. Okay, so what you declare now, an efficient learner, is essentially given for a concept class C, is that you say, okay, this concept class is efficient learner. If you have a classical, if you have an efficient learning algorithm that basically allows you, with polynomially many inputs, training samples, allows you to predict what, achieve a very high test accuracy with, say, 99%, where the evaluating the classifier is efficient and training the classifier is efficient. Okay, so in order for us to basically show that in this setting you can actually generate such a learner, we need to go and embed a problem that is sort of a hard problem for a classical computer. And one of these, the standard problems where you know that a quantum computer does have an advantage in solving the problem over classical computers, is the discrete logarithm problem. So the discrete logarithm problem, what you're asking, so given a generator of Z star P, you're handed an element Y, and you want to know to which power within Z star P do you have to raise G so that that you match y. So you want to take the discrete logarithm of y with respect to g. And so most of the standard cryptography tools, schemes, this is a classical one-way function. They're based on the hardness of this thing. So it's generally not believed that there is a classically efficient algorithm that allows you to do that. And so based on that problem, we now go and try to construct a classical data set that will be hard to learn for a classical classifier, but a quantum classifier using these kernels could learn. Okay, so one data set, if you just look at Z star P, sort of in log space, and you just draw a line through it, you separate in two sets, then you assign a +1 label if one of your if log gx lies in the left side of the set, or if you assign a -1 label otherwise, then that's actually in principle a pretty easy learning problem. So if you have only access to that, there are presumably a lot of classical learners that can learn that. But the trick is now you try to obfuscate the entire thing using the exponentiation, modular exponentiation with G. Now, for any typical classical algorithms, these labels now look very, very much random, and it's going to be very hard for a classical learner to basically apply the initial learning algorithm. We said just cluster to the left, cluster to the right. Okay. However, so if you could solve that, however, convert this. So if you were to run Shor's algorithm and then basically get out the be able to compute things in log space, that's probably an easier problem again. So that's a good starting point to see whether the quantum machine, the kernel method, is actually able to solve that as well. Okay. All right. So the thing is now we know, okay, there's one way of solving it, but just predicting the label of whether you're on the left or the right of that in that set, is that hard? I mean, we know that taking the logarithm, this discrete logarithm, is hard. We believe that. But just predicting one bit of this entire thing, is that hard? And so what you can do is you can actually show that, yes, just trying to guess, having a learner that after seeing sufficiently many training samples is able to guess the label correctly with slightly like 1/2 + 1 over polynomial in n, where n is sort of the log of the prime success probability, is going to be allow you to, in principle, solve the complete discrete logarithm problem. So this is a result that we adopted to our setting from Bloom and McCauley. And so what you can show is basically the basic idea is how you reduce it. I'm not going to go through the proof, but the basic idea is basically that it's sort of easy or polynomially efficient to compute roots of g of x, so of your y in the module in Z star P, and so the only thing you have to decide then is basically whether which branch of the root you have to pick on a high level, right? And so if you could do that, you could learn one bit, and once you learn that one bit, you can proceed going and learn more and more bits of the actual logarithm. And that would allow you to actually solve the complete discrete logarithm problem. So if you're able to, after having a learner that is actually able to predict with a bias more than 50% what the correct label is, you could start boosting that using a method by Bloom and McCauley to actually completely learn the discrete logarithm of that particular data sample. So meaning that if you have now a classifier that could solve this problem classically, you'd also have an efficient classical algorithm to solve discrete logarithm. Okay. So as I said before, a trivial algorithm exists by basically using Shor's and then just clustering the data left and right, because then all the hardness essentially sits in the fact that you've just gone and obfuscated it. Now, the question is now, okay, we know we can do that, solve that using Shor's, but with that entire feature map setup that we've been looking at, is it possible to actually, within that framework where you say, okay, let's estimate the kernel, solve the classical support vector machine and so forth, does that allow you to efficiently, from start to finish, have an efficient learner? Can you formally show that? And so that's what we did. We used a circuit that was used in the context of statistical zero knowledge proofs by Dorita Harnoff and Tashma. And so what you can see is that if you use these states as sort of your feature state, there's a polynomially efficient circuit that prepares them. Then these interval states basically, they cover certain intervals where your basis sits, and then you walk around, and you basically have that allows you just having the overlap between those. it gives you a certain margin property, which allows you to essentially to train the to train the classifier efficiently. So you can run through this, and there's depending on how large you choose k, that determines how wide the margin is around which you try to classify, and based on that you can show the following, that the actual algorithm that you would run where you prepare these things, these states, you compute the overlaps, you estimate their the kernel entry, you draw up to an additive error. That's the interesting bit, and have a support vector machine that then learns that thing. Basically, you actually achieve arbitrary good classification accuracy with polynomial resources. And so, what are some maybe some components we'd have to point out where this deviates a bit from what people worry about classically, and that's basically due to this additive sampling error that you have in estimating the kernel function, right? Because you only take if 1 over epsilon squared many shots, and you have per kernel entry you have an error epsilon. And now you have to worry about, is actually the convex optimization problem, is that still robust to that type of perturbation? And then within the actual generalization bound, to where you start to bound the actual accuracy, also in the evaluation of that learner, you have to take into account the classification error and the actual statistical error, and since it's a threshold function, that's a bit delicate. But since these states are constructed so that you have such a margin property, you can show actually that this is robust. And so since I'm at my 20 minutes, so you can view these quantum kernels as sort of general heuristics that people can try out and for these shallow circuits. And for one specific problem that may not be practically relevant, you can actually formally prove a separation between what you can do classically and quantum mechanically. And but I have to point out that example is, as I said, neither particularly practical nor is it particularly near term, because the circuit that you would run is still cubically long. It's sort of very much puts you into the error-corrected regime. But at least formally, you know that this approach is not immediately dequantizable and immediately trivial. Okay, I think with that, I'm at my 20 minutes, and thank you very much.